Hi, welcome to another lecture on college physics. Again, we're in chapter 2, and we just finished talking about velocity. We defined instantaneous velocity and average velocity. Now we're going to go ahead and define acceleration, and once we've defined acceleration, we're going to be in a good position to develop the equations for 1D kinematics that will be valid for a constant acceleration. And then with those worked out for ourselves, we'll go ahead and solve a few example problems. So to get into our definition for acceleration, we'll go back and look at our friend here. And by the way, we're getting pretty close to the end of having to look at our friend Mr. McDougall. We won't need to look at him too much longer. We've already talked about this position and velocity chart, and we know what position means. That's just where he is at any given time. And his velocity, well, what they're plotting there is the instantaneous velocity. That's how fast and the direction he's going at any given time. We've defined that. And then there's this new term down here. Well, it's always been here, acceleration. So what is that? Well, you already may have some idea that acceleration is the rate of change of velocity. The velocity, we define that to be the rate of change of position. And now we have the acceleration. We're going to see that's just the rate of change of velocity. And if I start moving him around, we can see, okay, so his position versus time, we can always see what that is here, the blue curve, position versus time curve. And also pretty jiggly, even more jiggly it looks like on the graphs of the simulation, the velocity and the acceleration jiggle around. So the instantaneous velocity and the instantaneous acceleration tend to be non-constant. We've talked about the definition of the velocity. That gives us the rate of change of the position. Let's go ahead now and define acceleration. So here we are in our textbook, section 2.4, college physics textbook. And here we're going to define acceleration. Acceleration gives the rate of change of the velocity. And here we're going to define average acceleration. And we can see it's defined in a very similar way as the average velocity was defined. So remember, the average velocity is defined to be delta x over delta t. That is, it's defined to be the rate of change of the displacement. So here we see the average acceleration is defined to be the rate of change of the velocity. That is, it's delta v over delta t. So average acceleration is defined in a very similar way as average velocity was defined, except that what's changing is now the velocity and not the position. So remember, average velocity is defined to be delta x over delta t. That is the displacement over the time it takes to make the displacement. And here, average acceleration is defined to be delta v over delta t. That is the change in velocity over the time it takes to make that change in velocity. Again, delta just means final minus initial. So here, this is final, this is the initial. Change in velocity over the time interval it takes to make that change. And for us in college physics, we're always going to be considering the case of constant velocity. And here we can see that if we just start moving Mr. McDougall around here, that his position, velocity, acceleration, none of those are constant. Nonetheless, we're going to treat the case of constant acceleration almost all the time. And that, in fact, won't turn out to be such a limitation as it may seem. So if we recall, we saw that we can approximate Mr. McDougall's motion, like all this motion we're seeing right here, we could approximate that to a very good degree by considering his average velocity over different legs of his trip, different intervals of his trip. And that average velocity, as we recall, is the constant velocity that will get him to the starting and ending point of some interval, as the overall result of the variable velocity did do. And that gives us a very good simplified picture of his motion. And that was with constant velocity. And when the velocity is constant, what would that tell us about the acceleration? Well, if we look back at the definition of acceleration, we see that if the velocity is constant, the acceleration is going to be zero. So if the velocity is constant, that means the delta is zero. It doesn't change. The final is equal to the initial because velocity is constant. And therefore, acceleration would be zero during any interval where the velocity was constant. Now, if we were modeling this trip, as you might recall, the velocity couldn't exactly be constant in the sense that we would have to make it different values. It would actually have to step to different values. So it could be constant along this part of the trip, and we could choose another constant along that part of the trip. But the velocity would have to jump from one value, from one average value to another average value over different legs of the trip. For example, between here and here, we'd have one value. Between here and here, we'd have another value. Between here and here, we'd have another value of velocity. And the velocity would have to jump, step jump. So it would be one value here, then step jump to another value. Something like this. We could model a trip, start them off like that, then give them another value of velocity, then give them another value of velocity, and we could give them another value of velocity. And we could recreate a trip. These are all these, straight lines. I could give them another value of velocity. Oh, he ran into the wall. Anyway, you can see what's going on here. If I did it just right, I could recreate any trip I like, any position versus time curve, even though it was curvy. I could approximate it with these little straight line segments. Each one of those has constant velocity. Then at any place that the velocity is constant, as you can see, the acceleration has to be 0. However, when the velocity changes, let's say from between this point and this point, velocity changes, the acceleration can't be 0 right there. And you can see what happens. Well, the acceleration suddenly kicks on in those places. So anytime the velocity changes, the acceleration kicks on just for a second. So here the velocity increases, so the acceleration has to bump up just for a second. Here the velocity decreases, well, the acceleration has to bump down. So the acceleration is a vector. Just like the velocity is a vector, acceleration is a vector. Because velocity has a direction, and when you look at a change in velocity, that's also got a direction, so acceleration also has a direction. In 1D, that direction is completely specified by the sign. So if the acceleration is positive, that means the change is to the right. That means velocity is increasing to the right, or in the plus x direction. If acceleration is negative, that means the change is negative. That means velocity is changing in the negative x direction. So you can see exactly what that means here. Here the acceleration is positive, the velocity jumps up. Here the acceleration is negative, the velocity jumps down. And by down, I mean it's now going in the other way. It's going, let's do playback. It's going to the left. When I say the velocity jumps down, I mean the velocity switches to the left, or to the negative x direction. Okay, so in this case we're approximating a trip with constant velocity. Now we could increase our sophistication just a little bit, get some curviness to our model by, instead of considering only constant velocities and pretty much 0 acceleration everywhere else, now we're going to consider constant acceleration. So here we could make trips with constant acceleration. So for example, I'll start off the acceleration like that, and then now let's make it, and then you can see I'm trying not to let him hit the wall. Oh, I think maybe if I go this way again, and we can slow him down a little bit, and then maybe make it 0 now. And so you can see the kind of trip we're making here. So now I have a more curvy path. The velocity is no longer constant, but we're just considering different values of constant acceleration. And in actually most of the cases we're going to look at in college physics, we won't even be considering anything as complicated as this most of the time. So in this case, we're just considering constant acceleration that just step jumps at various points. And we can see when the acceleration is constant, what happens with the velocity. When the acceleration is constant, then the velocity just changes all along a straight line. So the velocity versus time profile for a constant acceleration is linear. That is, it lies along a straight line. Just in the same way that when the velocity is constant, the position versus time profile is linear. And we're going to see pretty explicitly in just a second here how that is consistent with the equations. And most of the time, we're just going to consider one value of constant acceleration. We're not even going to make the acceleration step jump up and down at different places like we've done here. We'll just consider one value of constant acceleration. For example, we could consider, I'll give them an initial velocity 5 and then consider a value of acceleration of -10. We can see what his motion would look like in that case. We'll do playback. So that's his position versus time, velocity versus time, and acceleration versus time constant for the case of a constant acceleration of -10. So that means his velocity is changing to the left. That is, every second that goes by, he's gaining speed, but in the negative direction. And there are some very important examples, real-world examples, that are important to consider of constant acceleration. Physical real-world example of constant acceleration, very important example of it, is acceleration due to gravity. It is a fact that near the surface of the Earth, all objects are accelerated due to gravity at a rate of 9.8 meters per second squared straight down. You've experienced this, well, you're always experiencing this, but if you ever jump up in the air, you'll experiencing that, you'll start accelerating straight down at 9.8 meters per second squared. Or if you throw a rock, that rock will immediately begin accelerating down 9.8 meters per second squared. So it's a very important example of a real-world case, constant acceleration. And even if the acceleration is non-constant, a lot of times the acceleration can be approximated as a constant. Just by considering the average acceleration, you can get a very good approximation to the motion. For example, if you're driving your car and you start at a stop sign and you accelerate from rest at a stop sign, you push your foot on the gas, your car will approximately accelerate at a constant acceleration up to the velocity, the final velocity you like, say 30 miles per hour or however fast you want to go. That acceleration will be more or less constant. You could certainly approximate it as constant. So there's many cases, many interesting examples where we can consider a constant acceleration. Now that we've defined acceleration, let's go ahead and use our definition of acceleration, and in particular for the case when acceleration is constant. That's the case we're going to mostly consider. So we're going to develop a set of kinematic equations known as the 1D kinematic equations, which can also be extended to 2 and 3D. And we're going to develop this very useful set of kinematic equations, very useful for describing motion. We'll develop them, and then we'll use those kinematic equations to solve some example problems. So we have our definition of acceleration, it's average acceleration, and we'll put the overbar over it, so overbar means average. And it's defined to be change in velocity over the time it takes to make that change in velocity. So that's final minus initial, and I like to call the final just v and the initial v0. We could put an f there. I mean, there's so many different notations, and sometimes one notation could be better than another. However, this is the one I prefer. If there's no good reason not to use it, I'll go this way, final minus initial time. And so that's our definition for average acceleration. Remember, the average acceleration is like the average velocity, in the sense that the average acceleration is the acceleration that will give you the same change in velocity over the same time interval on average as the net effect of a variable acceleration did do. So a variable acceleration could give you a change in velocity over a change in time. And that variable acceleration, of course, is not constant. But you can always find the average acceleration, which will be the constant value that will give you that same change in the same time interval. The velocity profile won't look exactly the same in between, but the starting and end points will be the same in that time interval. And so now this is the one we want to consider. So I just want to assume that my acceleration that I'm going to consider is my average acceleration, and just take that to be constant. I think this is my approximation that I'm always going to want to use. And a lot of times this approximation could be not even an approximation at all. It could be absolutely what's going on. For example, in the case of acceleration due to gravity, near the surface of the Earth, the acceleration due to gravity is constant, 9.8 meters per second squared down. A lot of times when you're accelerating in your car, if you're accelerating from 0 to 30 miles per hour in 15 seconds or so, your value of the acceleration while you're speeding up right there probably pretty roughly constant. And if it wasn't, you could approximate it as constant to a very good degree. May not even notice the difference. Okay, so that's just what we're going to do. We're just going to say acceleration is going to be the average, and I'm just going to throw away the over bar. I'm not even going to bother to write that anymore. And another thing I'm going to do here when I start developing my equations to simplify things is just take the initial time to be 0. If the initial time is equal to 0, then that's going to tell us also then if t0 is equal to 0, then my delta t is equal to t. Right? So delta t is t minus t0, but if t0 is 0, then delta t is just equal to t. And what that implies is that we're using a stopwatch where we start the clock whenever we begin the action of whatever we're interested in. So if we're interested in accelerating from rest, say from 0 to 30 miles an hour in 15 seconds, say that's the example, then we start the clock as we begin accelerating. So the final time, 15 seconds, that's just when we stop the stopwatch. The stopwatch starts at 0 and ends at 15 seconds. T is the time interval. So that's just going to simplify our notation. So in that case, then I have my equation now just becomes this. It just becomes, okay, final minus initial velocity over the time. Now what I'm going to do with this equation is I'm just going to solve it for the final velocity. So here I'm going to assume that the initial velocity and the acceleration is given, let's say. Kind of think this way, given the initial speed, say if you start at rest, then that would be 0, v0 equals 0. That means start from rest. So we're going to assume v0 and acceleration are given, and you want to find the final velocity. And you have this equation right here, our simplified equation. So just solve for the final velocity. So how do you solve for this algebraically? Multiply both sides by t, and then so the final velocity is going to be at plus v0. Okay, what I did is I just multiplied both sides by t, and then moved the v0 onto this side of the equation. Or I could write it this way, v0 plus at. Okay, so velocity is equal to whatever it starts off at plus at. So this tells us that the final velocity is equal to whatever the initial velocity is plus the acceleration times time. So the acceleration times time gives us how the velocity is changing in time. So this is one of our first kinematic equations. It gives us the final velocity given the initial velocity and the acceleration for any time. So if we know this, we know the initial speed, say 0 if you start from rest, and we know the acceleration, say 5 meters per second, then we can find the final velocity given any initial velocity and acceleration. Then we can find the final velocity. Before we start to play around with this and use it in calculations, I want to get one more kinematic equation up here for us, another basic one, that comes from the definition of average velocity. Remember our definition of average velocity, v average. That's equal to the rate of change of the position, or the displacement, over the time it takes to make that displacement. And here we're going to be using this assumption that t0 equals 0. That is, we're using a stopwatch, and we start the stopwatch at the time of interest. So the action always starts with t0 equal to 0. So this then becomes final minus initial, x is the final, x0 is the initial, over t minus t0, t0 is 0, so it's just t. And again, here I'm gonna assume that we're given the initial position and the average velocity, say. And we want to find final position. So here we wanted to find final velocity, here we want to find final position. So to do that, just do the same procedure. Solve for x. So all I did was just solve this equation up here for the final position x. Just multiply both sides by t, and then move the x0 to the right side to put this x all on one side of the equation. And this is the answer you get. Final position x is equal to x0, wherever it is when you start the clock. Because you can see if you put in t equals 0 right here, then 0 times v, whatever it is 0. So the initial position, so when you start the clock at t equals 0, then x is just equal to x0. Then x now adds whatever the average velocity is times t. So what kind of a curve is this going to give you? So the position versus time curve, for this particular case, for x as a function of time, position as a function of time, will be a straight line. Can you see that? What would be the equation of a straight line? Equation of a straight line will be y. Y is equal to mx plus b. So, okay, I'll write it this way, b plus mx. That's the equation of a straight line, if you remember from algebra. Here, x is playing the role of y in this. We can see x0, that's playing the role of the y-intercept. And t, that's actually playing the role that x had been playing in this equation down here. You can see right here, x and t are swapping out, x0 and b are swapping out, and x and y are swapping out in what roles they're playing. So what does that mean? It means that the average velocity is the slope of the line. So you can see m is the slope of the line, of this line down here. Well, average velocity is the slope of this line up here. So this is a linearized position versus time curve. And this position versus time curve in the time interval of interest will give you the same starting position and final position in the interval of interest, say 15 seconds, that the actual position versus time curve did if it was not a straight line. Say it could have been curvy. So for times in between, and maybe times before and times after, the actual position, initial and final position don't necessarily match. But at the starting time and the final time, the initial and final position of the position curves match for this linearized version and whatever the real version was. And maybe this was it. Maybe the velocity was just constant. Anyhow, here's our first two kinematic equations. I feel like labeling them. I'll call this 1 and 2. Now there's actually just one more kinematic equation that we're going to need that will actually complete our description. Give us a complete kinematic description for kinematics in 1D a la Chapter 2. So that equation's coming up. To motivate the statement of the final equation, the final kinematic equation we'll need to complete our description of kinematics in 1D, let's solve this problem, this example problem. So here's a problem statement. Car accelerates from rest to a cruising speed of 30 miles per hour in 15 seconds. What is its acceleration? Okay, well here we have an equation that gives the final velocity in terms of the initial velocity and the acceleration and time. Let's see what we know here. Car accelerates from rest. That means v0 equals 0. That means start from rest means your initial velocity is 0. So we got that one. The time that's going to take, okay, we're given that time interval 15 seconds. So now we can simplify this equation for this particular example. Final is just equal to acceleration times time. Here the time would be 15 seconds. I'm not going to put that in yet. They're asking me part A, what is the acceleration? Okay, so to solve for part A, we solve our simplified equation for acceleration. So here, what's it going to be? Acceleration is just going to be equal to, solve for it, the velocity over the time it takes to come to that velocity. Okay, I have the velocity and I have the time it takes to come to that velocity. I have the acceleration then is equal to 30 miles per hour in 15 seconds. So I can even do this much math in my head. I can see that that's equal to, so 30 divided by 15 is 2 miles per hour per second. Okay, so is this a good description of the acceleration and useful? Absolutely. What does this tell us? This tells us that the car is gaining velocity at a rate of 2 miles per hour per second. So that means every second it's going 2 miles per hour faster than it was the previous second. So here it's going to take 15 seconds. That's actually quite a long time. That thing is really going slow to accelerate to 30 miles per hour. So what's going to happen? So at the 0 time, it's going 0. After the first second, how fast is it going? 2 miles per hour. At time 2, second, it's going 4. Time 3, 6, 8. All the way on up. So every second, it just keeps adding 2 miles per hour more to its speed until 15 seconds has passed, and then it comes to its final cruising speed of 30 miles per hour. And when I say cruising speed, what does that mean? It implies that now it's just going to be going at constant velocity, constant speed of 30 miles per hour after that. Is this SI units though? What if they had asked for it in SI units? Let's say they'd thrown that in. You know, it's probably going to be on a test, and then they're probably going to go, okay, I want it in SI units. Even though we go, okay, well, this description is great. Actually, when we get the answer in SI units, we'll see that just for our ordinary understanding of driving, this description is perfect. Miles per hour per second. That really gives me a nice graphical, clear description of what's happening that I can easily understand. But anyhow, to convert it to SI units, what do we got to be able to do? Well, here I got miles per hour per second. So for SI units, what do we have? So for SI units, I need all my lengths in meters and all my times in seconds. So I need to convert between miles and meters. So here I'm looking up online and I'm saying that 1 mile is equal to this many meters. I think I'm just, this is a lot of precision. I think I'll just go with 1609 meters is equal to a mile. So we have 1609 meters is equal to a mile. We're going to be using that in our conversion. And another conversion factor we're going to need is we're going to need the conversion factor between hours and seconds. You can verify for yourself if you don't already know how many seconds there are in an hour. It's 3600, 60 times 60. 3600 seconds in 1 hour. So there's our conversion factors. So let's write our acceleration so we can convert it. It's equal to 2, I'm going to write it this way explicitly, miles per hour. This is more conventionally mph, but this explicit way is going to help us convert it, and then 1 over a second. So now what do I need? So I'm going to need to use my conversion factors. So first off, I want to get miles into meters. So I'm going to use a conversion factor there. So I'm going to make, remember, a magic 1. Divide both sides of this equation by 1 mile, and what you'll get, if I divide this by 1 mile, then I'll get 1 mile over 1 mile is 1 mile over 1 mile. So whatever I do to one side of an equation, I have to do to the other, and that's all equal to 1. This is all equal to 1. So now I multiply this by 1. Okay, anything times 1 is itself, but here I'm going to multiply it by this magic 1. It's not really magic. It's what they call a conversion factor. Maybe it'd be more explicit to call it a conversion ratio. Then we can see what's going to happen here. Miles going to cancel with miles. So those will cancel. So now what units would we have overall? We would have 2 times 1609, whatever that is, meters per hour second. But we don't want hours, right? We want seconds is our unit of time because it's in SI units. SI unit of time is a second. So I need to convert the hours into seconds. So what conversion factor am I going to use here? So let's see, I'm going to want hours on top, so that hours cancels with that hour. So I have an hour is going to be equal to 3600 seconds. Then we're going to see hour, that hour will cancel with that hours, and what's standing? It's going to be meters times seconds times seconds. So that's going to be meters per second squared. Now the job is for our calculator, and I get 0.894 rounded. And it's meters times seconds, so that's meters per second squared. So that's the acceleration in SI units. So in SI units, it's 0.894 meters per second squared, or meters per second. That's another way we could write it. Meters per second squared is equal to meters per second. So what is that telling us? That's telling us that every second it's going 8.94 meters per second faster than it was the previous second. It's just like what we had up here. Here every second he's gaining 2 miles per hour. And here every second he's gaining 8.94 meters per second. So 2 miles per hour per second, to my mind, was even more comprehensible than this because I'm more familiar with miles per hour when I'm traveling in my car than I am with meters per second. But anyhow, that's the relationship. Okay, so we solved part A. What is its acceleration? And we have it in both this kind of units here, miles per hour per second, and in SI units, meters per second squared. Now, how far did the car travel during this 15-second interval? Okay, so that's another question. How are we going to handle that? How far did the car travel during this time interval? Let's see. So for that, what do we have? We have x equals to, okay, x is wherever he starts off at plus average velocity times time. Okay, well, we could say, let's say we could say x0 equals 0. You know, you might as well do that. Just say, okay, you know, the arbitrary 0, the x-axis, when the car starts accelerating, we just put that to 0 just to simplify our notation a little bit. Then what do we have? Then any time after that, your position is just going to be your average velocity times time. Okay, but your average velocity, now average velocity is the constant velocity that will give you the same displacement over the given interval. However, an average velocity is a constant velocity. And he was accelerating, definitely accelerating, right? Here's his acceleration, kind of close to 0.9 meters per second squared. He's definitely accelerating. So what does that say about his velocity? His velocity is not constant. So how are we going to find his average velocity? Well, what we can say is, and this is always true, when acceleration is constant, then the average velocity is equal to the final velocity plus the initial velocity in consideration divided by 2. It's the average of these two. Now that's only when the acceleration is constant. I haven't proved that here, but I can demonstrate that it's true for a couple of cases. Let's do that. Let's just show that it's true, and then once we're confident in it, then we're going to go ahead and use that to solve the rest of this problem. And by the way, this equation that I just wrote down is the third equation that's going to complete our description of kinematics. We'll call that equation 3. Now, I call that a complete description, and it is. With this equation, so equation 1, 2, and 3, as I've labeled them here, that is a complete description of 1D kinematics. However, we can cook up several other equations from these equations. 2 in particular we're going to derive from these equations. So if you remember your algebra, for every equation you can solve for one unknown. So for each one of these equations we could use to eliminate one of the variables and introduce that into another equation. So we're going to go ahead and use that to get some different forms of the equations that turn out to be pretty useful. But before we get to that, let's just verify that this is actually the case. The average velocity for constant acceleration is just what you might expect an average to be. That is the sum of the things that you're averaging divided by 2. There's 2 of them. Let's add them together and divide by 2.